overall microstructure and also to the IT or TTT diagram. We have discussed a little bit about that last week, but we will give it more understanding on that matter again this morning. If you have any question from the previous lecture, I will happy to answer. If not, then we will continue. So today we will talk about the effect of alloying element, and this one we should start with annotation. Okay, so the effect of alloying element, and then my pen is not working. I don't know why. Okay. Okay, so this and a little bit about the mechanism of straightening, or how we straighten metals, which is basically we have discussed these topics in metal 1, but we will a little bit review about this, and we'll correlate this thing to the IT diagram and how the behavior of a metal, if it is hardened, or then we discuss about hardenability. We know the hardness in metal 1, but now we are talking about the ability of material to be hardened. And that's why we call hardened ability. Okay, hardened ability. So this is actually the capacity of material to be hardened, and this can be assessed with several methods. One of that it is a Jomini test. We discuss about the Jomini test, how we perform this thing, the test, and what kind of result, and how we can read result from the Jomini test. Okay, so this is basically the general idea. So if we have a composition of steel sample, composition of steel or metals, metal sample, which is what I means by composition is, for example, the percentage weight of carbon, and the percentage of weight of manganese sample, and the percentage of chromium, nickel, etc. Which is inside the steel, we call it the composition of steel. So this composition, and this composition give metal microstructure basically, yeah. And this is depend on the manufacturer, of course. This is one step here, which is manufacturing. It is, for example, either this is by casting or forming will give different microstructure. And then anyway, this can be processed for further modification. We call it this processing or modification. We call it modify this thing, modify or treatment or processing. And we during the processing, we use this diagram to help us or to guide us into the situation or into the prediction of what kind of microstructure that will result by the modification. So as we already learned, for example, if we would like to have martyrdom, then we have to quench the sample very fast, and it should be in front of the critical cooling rate, so in front of the nose. However, if we would like to have perlit, then we cool it quite a bit slow, either in the air or in the furnace. So we keep it the sample inside the furnace. We turn off the furnace and let the furnace cool down by itself. That's will give some kind of slow cool, and then slow cool will give you perlit microstructure. So this is guided by the TTT diagram, and from those diagram we know the MS, which is Martensit start and Martensit finish, and how much Martensit, as we discussed last week, it's depend on at which temperature we quench the sample. So this quenching temperature is very important to determine how much Martensit we have. So then we have alloy with modified microstructure. Okay, then which means that this also optimize mechanical properties. So basically, the idea of changing composition, for example, how much carbon, how much manganese, how much chromium, it is actually to optimize mechanical properties, right? So the idea is that depend on the application and depend on what kind of mechanical properties we expect, and then we optimize the composition. But it's not only the composition that is affected to the mechanical properties, but also the microstructure. And the microstructure optimization then become important to further modify the mechanical properties. So in summary, basically there is two ways. The first is to change the composition. The second is to change the microstructure by changing the processing or treatment. In many places we call it the heat treatment, because in many cases also that the treatment is involving heat. That's why we call it heat treatment. So this is modification is treatment, or this processing is treatment, and this treatment is involving heat. That's why we call it heat treatment. So in some cases they are involving also some mechanical. That's why people also call thermomechanical treatment sometimes. Thermomechanical. So it's not only thermo, which is heat, but also some mechanical treatment. So that's why we call thermomechanical treatment. Okay. Okay, we continue. Yeah, so that's why we need a phase diagram here, and also one of the other diagram is not only phase diagram, but this is IT diagram. Okay, IT or TTT or CCT diagram. Yeah, this three things is necessary for us to know before we do modification. Okay, so then this is also general concept. If you learn from metallurgy one, that if you adding nickel, for example, into the iron, yeah, if you have iron here in, for example, in body centered cubic structure, which is alpha iron, or we call it ferrite, okay, BCC alpha iron. If you put carbon, which is alloying element 2, basically, will sit in the interstitial, right? Interstitial can be somewhere here. You have carbon here. Then you have ferric. You have ferric. But you can also, in addition to the carbon, here it's carbon, here is iron. You can also add another thing, for example, nickel. We have nickel here with this color, orange nickel. You can add nickel. So how if you add nickel, because nickel have a similar size, close to the iron, so we call it a substitutional alloying element. It will actually replace one of these. So we can actually remove this thing. Okay, and this will replace actually this thing. Okay, will replace this thing. So this is called substitutional alloying element. It's called substitutional. Substitutional. So which mean they are sitting in the atomic lattice of iron, okay, basically, and then because nickel will there or will sit there or will take a position of the atomic position of iron, and they are basically not regular. So nickel can be here in sometimes, can be here, can be here. So basically random situation. That's why we call it dissolve randomly, and then we call it a solid solution later on. So this dissolve in iron, and then it is basically random, and then we call it solid solution. Solid solution is still alpha with nickel as alloying element. Okay, alpha containing nickel. So this is basically dissolve, and then as we know that dissolve element will increase strength of the phase. We learn in Metal 1 because this interaction of microstrain or microstress inside the microstructure and increase the strength of the phase. Whenever you have an increase on the phase, it means that in total, in macro, strength will be also increased. And then in other situation, if you increase more and more nickel or in more and more other alloying element, for example, chromium or nickel, also other alloying element, then they will be saturated. It can be saturated situation. So there will be saturation of alloying element. So then whenever it is saturated, then as you know that, for example, they will saturate means too much, too much. There will be no not random situation anymore. Then it become precipitate, so forming precipitate. So they are form another phase. So if this is too much nickel, for example, and there will be formation of other phase here, which is, for example, let's take very specific nickel here, and then nickel is arranged in regular like that, and then this become some other compounds here. Okay, other compounds. Okay. Okay. So there are two scenarios here. So for alloying element, the first is dissolve into the phase, and the second is forming another compounds, which is we call it precipitate sometimes, because it is mainly between a main phase. So if you have a microstructure like that, which is containing grain boundaries here, containing grain boundary. And usually the second phase, which is something form, we call it precipitate because usually form in between main phase, something like that. We call this thing precipitate. Okay. Because the morphology is nothing to do with chemical or thing like that, but it's something to do with the morphology because they form between something else, which is the main. That's why we call it precipitate. And then, as you know, also precipitate also increasing the strength of microstructure because it will be hinder the movement of dislocation. If you remember that the strength of alloy or element is based, phase is actually depend on the movement of dislocation. Okay, anyone remember that thing? If you hinder the dislocation movement, it means that you increase the strength of materials. That's the idea behind the strengthening mechanism. The second idea, basically, the first idea you dissolve element, and the second is okay, and either this is dissolved in the phase or it will form the precipitate. Actually, it will change the equilibrium phase diagram. Okay, the first it will change the equilibrium phase diagram. So, for example, the eutectic point is not at 723 anymore. It's not here anymore if you have a higher amount of chromium, for example. So that will be changed. The actually the phase diagram is changed because if you add more and more chromium. Okay, and also the second thing, it will be change the IT or CCT diagram. So remember from the class last week that it will be shifted in general. Alloying element will be shifted the TT diagram to the right and down. So MS will be down, decrease, and then the nose will be shifted to the right. So basically, the TTT CCT diagram will be shifted to the right, which means that if it is easy for you to make a Martin sheet in the alloyed in the alloying in the still with the alloying element. So increasing chromium will ease you or will make it easier to form Martin sheet. Okay, if you have any question, you little bit keep still. Thinking about this, and then if you have any question, we can actually discuss.
Hello, sir. I have a question.
Yes, please.
Is it possible to there is a crack when we quenching too fast?
That's possible. I will explain later on. And it is somehow covered in the slide. I think in the end of the slide will be some slide why it is occur. Yeah, Timothy, I will point on that in the end of the lecture. I think it is in the slide already.
Okay, sir.
Okay, as I mentioned before, there are possibility of alloying element to be dissolved in ferrite and making other compounds. Okay, and these compounds can be many form. Okay, and then basically that's other terminology that we can use. But first of all, let's discuss one thing. Okay, they will dissolve in ferrite. Okay, dissolve mean they will be randomly um, distributed in the microstructure. Dissolve in ferrite. For example, nickel and silicon. Nickel and silicon is prefer to dissolve rather than making any precipitate. But if there is too much nickel, there will be formation of nickel aluminum. This is a compound. This kind of regular atomic structure of nickel, which is 3 atoms of nickel with 1 atom of aluminum. So something like this. And then this is making compounds. Atau bahasa Indonesia senyawa ya, compounds. And then we'll take also another example, which is manganese. Manganese, see, this is this arrow tell you that the probability of manganese inside the microstructure will be dissolved. However, in some situation, it can also form carbide, okay, with this microstructure. We call it carbide. It is something with carbon, because we know that the steel is actually carbon steel, always carbon present in the microstructure. Therefore, there will be high possibility for formation of something like this: iron plus alloying element in this case, and then plus C. Anything with C, we call it carbide. Okay. 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 Okay, then it also similar with the other, for example, chromium. See, the chromium is tend to dissolve. However, it's too much, there will be also formation of carbide. Molybdenum, tungsten, vanadium, titanium. See that titanium is the arrow is going to there rather than here. So basically, if you add titanium, there are prefer to make a carbide rather than dissolve. So which means that if you put titanium here, for example, you put titanium atom somewhere in the microstructure, they prefer to make some kind of titanium carbide in the grain or inside here rather than dissolve it. So they will make it titanium carbide. Instead of dissolve, they will prefer to form titanium carbide. But later on, we will also probably discuss what is different between the two. But this is the tendency for the titanium to make carbide rather than dissolve in ferrite. This is in ferrite. So aluminium prefer to dissolve, copper also. So this is some example of how distribution of alloying element in carbide. Okay. Sorry, in ferrite. In steel, for the effect to the past stability, or in other words, in the term of phase diagram, how alloying element behave into the phase diagram, or the effect of alloying element into the phase diagram. That's why if we talk about the stability, and then there is element that is actually stabilize ferrit. Okay, which means that they are prefer to dissolve in ferrit and stabilize the phase. And then also alloy that is stabilized austenite and dissolve in stabilized austenite. I will explain later on, maybe in the next slide, what does it mean. Okay. Maybe we need to jump to the next slide before. And then there is also a carbide forming element. That's also carbide stabilizing element. And also there's something called nitride. So basically, if we make some kind of group, okay, group, there will be three group. Okay, one is something like that, which is stabilized phase, either ferrite or cemented, which means that they are preferred to dissolve. And then something that is like to form a carbide. This is the second group. And then the third is something with to do with nitride. It is something with another type of steel that is contain nitride. So this is actually a different group. So this is different group. So this to make it easier for you to think of. So I will divide into three. First of all, it is something that easy to stabilize the ferrite, for example, chromium, something that stabilize austenite, which is nickel and manganese, something that easy to form carbide, and something is not easy to form carbide. And then the fifth, it is something to do with nitrate, but it is only work for steel that's contain nitrogen. Okay, for example, stainless steel. We'll discuss on it. So this is actually I will jump into this phase diagram. Okay, that's discuss about. Well, later on we can also discuss this slide. Maybe the arrangement of the slide is not perfect yet, but you see that this is for normal phase diagram without any chromium. So there's no chromium, no nickel, no manganese. Okay, so this is just iron with carbon, and then the carbon content is different, which is actually written here. The amount of carbon is somehow something like that. So it is 0.8 here, 0.8, and this is 1, 2, 2, 3, 4, 5 weight% of carbon. So then the question is that how if we add more nickel into this phase diagram, as you mentioned, or how if we add more chromium. See, from the previous slide, we understand that chromium is stabilizing ferrite. What does it mean? It's chromium is stabilizing ferrite. So chromium will stabilize ferrite. Okay, what does this statement means? Means that chromium will make the area of alpha, which is ferrite, is wider, which means they like to form ferrite rather than austenite. So that's mean it means that the area of austenite will be shrinking if you add more chromium. So well, this is a condition of zero chromium now. What you see, and if we add if we add chromium, then probability is that there will be shifting, maybe the different color. There will be shifting of this line, something like that. So what does it mean? It means that the eutectoid point is not at 0.8 anymore because it shifted to the left, and then the eutectoid temperature is not 727 anymore, but they will be increased. Why? Because the area of alpha now increasing. This is the meaning of ferritic stabilizer. So the ferrit area will be increase. So let's see the real image of it. So this is chromium. Okay, this is. Please focus on that. Okay, you see that if you have zero chromium here, you have a normal situation where the eutectoid percentage of carbon is 0.8. So this is normal situation, right? You have 0.8% carbon where it can transform with eutectoid transformation. So from austenite into the perlite. However, if you add 5% chromium into the steel, which is you have alloy element with 5%, what happens now? Now the eutectoid is shifting to the left and go up. So now the eutectoid point is here. This is the meaning of stabilizing ferrite. So which means that the ferrite area now from this area, this area into that area. Okay, that's let's make it this thing. This area, and this thing means that it becomes wider alpha compared to the previous one without any chromium. So whenever you add more and more chromium, see, they will be increasing further on. So if you put 12% chromium here, then they will be increase further the eutectoid temperature from this temperature into this point. So if you increase the gate to 15%, you have this thing. Until you add quite a lot of chromium, like 19%, you have no austenite anymore. Okay. So in this situation, meaning that you will form basically only ferrite. There's no austenite can be formed if you add too much ferrite stabilizer like chromium and silicon molybdenum. Okay, then what do you think? What is the effect of this thing into the treatment process or into your IT diagram, for example? What do you think? Um, you remember? Um, if you have a IT diagram, something like that, and then you have curve like that, okay, this is should be austenite, must be austenite. Okay, that's important thing. So the things that can be formed martensite, it is must be austenite. It must be austenite. Only austenite, only austenite. So only austenite that can transform into martensite. So that's why you heat treatment. You put it the sample into the austenization. Which means that you need to form austenite before you can transform it into martensite. In other words, if you don't have martensite, austenite, you don't have austenite, then you don't have martensite. Okay. So in this situation, it will be difficult for you to make austenite, right? Because there's no austenite region. There's no austenite. So for very high percent of chromium, it will not possible to make a martensite. So that's why, for example, um, there will be some class of alloy that is too much chromium and cannot be transformed into martensite kind of steel. Why? Because it's too much chromium. In other words, if you would like to make martensitic steel, if you would like to make martensitic steel, what do you think? What do you think? What is in your mind? If you want to make a martensitic steel, then the chromium should not more than 19%. Okay, that's the case. So why? Because if you add, yeah, so the chromium content cannot be higher, cannot be higher, cannot be higher than 19, cannot be higher than that. It should be less than 19%. If it is higher than 19%, then you cannot form austenite, then you cannot form martensite. With that mean you cannot make martensitic steel. So basically the idea is connected, one to the others. Okay. You can think of a little bit, and then we will continue in 1 or 2 minutes. Okay. There is another way to see this from the perspective of phase diagram. In the left, you see the carbon content here, right? This carbon content. And in other situations, we can also, as you adding more and more chromium, we can also make a plot, which is this is a temperature, as shown there, and then this is not carbon but chromium. Okay, it's just a way to see it. So see that this delta is actually also like alpha. It's quite clear to alpha. And then the situation, which means that you will not have austenite somehow. The austenite region is only this thing, function of chromium. So which means that there will be limited area you work on to have the mathematic stuff. But I will not go deep into it. It's just another phase diagram, but not plotting carbon. Instead of carbon, you plot chromium. This is function of chromium. So this is actually iron chromium phase diagram. So this is another way to see it, that the area of gamma, it is shrinking because of you adding more chromium. Why that the case? Because as you see that the chromium is stabilizing the ferrite. Okay, and then how about putting more things that stabilize austenite? Okay, for example, nickel. On the left side, this is the same cases. Have the chromium, but now we change. Instead of adding chromium, we add nickel. We add nickel. So what if you add nickel? The situation is the same. It means that the first you change the point of your tectonic point now. This is without any nickel, and then you put more nickel, or example here 2.5% nickel. What is happen is that there will be eutectoid decreasing temperature. It's not 727 anymore, but it's less than that. It could be 700. It could be more less than 700. For example, if you're adding more manganese here. Here, yeah, manganese. It is 0.35 manganese, almost zero, and it's 2.5 here. And then if you put 9, then you have this line, which means that now the eutectoid is now shifting to the left and going to the down. It means that now the eutectoid temperature is less than 727 anymore. It's not like this thing. What does it mean? It means that also you see that this area is now is wider. It's increased now. The area is become larger. Uh, this is the meaning of stabilizing austenite. This is similar with chromium. Chromium is sinking the austenite, but manganese and nickel is expanding the austenite region. So now the austenite area is expanded due to because of manganese and nickel addition. This is the meaning of austenite stabilizer. Okay, make it wider. So which means that it's easier for you to austenitization of the alloy, right? In other situation, we can also look at different view. Now this is I think this is iron nickel phase diagram. Instead of look into the perspective of carbon, you see it in the percentage of nickel. You see, then we if you put more nickel here, you will have more austenite, even up to the room temperature. It does mean in this is room temperature like 25 degrees Celsius. So it is possible, basically. So this is our austenite region. Okay, this is austenite region. So you can keep austenite until the room temperature. If you add enough nickel, if you have enough nickel, you can keep the phase, gamma phase, to the room temperature. What do you think? What does it mean? I mean, for you, it means that if you would like to have austenitic steel, which is stabilized at room temperature, then you have it austenite, then you should add higher amount of nickel. Okay. And what do you think? It is difficult or easy now to make a martensit if you have high amount of nickel? Any idea?
I think
Maybe it's
it
very
is
easy,
easier.
sir.
Why it is easy? Why do you think it's easy, sir? If you have, if what do you think? There will be the answer could be easier or not easier. Okay, there will be two answers. You can look into the slide and see from this slide. Yeah, actually, you can say something from the slide from the on the right diagram on the right side. See that okay, it is easier if you have a nickel on this side. Okay, if you have nickel not more than this point, example, that is easier for you to make austenite and quench to make martensit here. But however, if you have too much nickel from here, then you cannot form martensit on this side because it's always stable at room temperature. Okay, it's not possible. So it means that if you add a nickel lupa ketua kelasnya siapa ini? Saya lupa.
Saya Pak.
Adim ya?
Ya, iya Pak.
Ya nanti lewat kamu ya kalau ada seperti itu, misalnya kayak ada temannya yang nggak bisa masuk setelah ada technical. Tapi kita udah sepakat 7.15 ya. Kalau nggak 7.15 nanti kita nggak saya admit.
Oh iya Sir. Itu ini Sir, ada lagi Sir. Ini Bayu sama Josia tadi juga itu terdisconnect Sir.
Ini terdisconnect ya, bukan terlambat.
Iya. Iya terdisconnect Sir. Barusan aja saya. Saya juga mau bertanya.
Silakan.
Kalau misal kita punya dua, misal penstabil ferrit sama penstabil austenit itu kira-kira dia bakal cancel out atau gimana, Sir?
Iya, saling cancel out. Nanti total ekuivalen yang kita bicarakan nanti. Ekuivalen nikel sama ekuivalen chromium. There will be two things because we are mostly talking about chromium as ferrit stabilizer and nickel as austenite stabilizer. So everything will be sum up. Sum up means that it can be cancel out each other, but there will be total, and we call it equivalent. So there will be carbon equivalent and nickel equivalent. This is somehow we can find it somewhere in the books or in the internet, but basically this is empirical. Means that they get the equation from the experiment. It's not, there's no theoretical still yet. There's no theoretical calculation, but empirical. Empirical, what is mean empirical? Empirical, you do experiment, means that with kind of different content of carbon and different content of nickel, and you do experiment at which temperature each alloy is transformed, and then you make an equation based on that experiment. That's why we call it empirical equation. Jadi nanti ada ini ya, ada karbon ekivalen, ada chromium ekivalen, ada nickel ekivalen. Gitu. Nickel ekivalen itu maksudnya kita sum up semua alloying yang mengandung nickel, kita juga sum up something mengandung chromium gitu. Nah nanti dua itu kan saling berpengaruh ya, saling berpengaruh. Dan ini interact each other, jadi memang saling berinteraksi gitu ya. Nah interaksinya ini not clear enough gitu theoretically, tetapi ada persamaannya. Yang itu diderive dari empirical. Nggak tahu nanti apakah ada di slide saya ini. Kalau nggak ada silakan coba dicari internet, kalau minggu depan kita diskusikan kalau kamu ketemu ininya. Nanti by time kita lihat ya. Tetapi jawabannya adalah in short there will be not totally cancel out each other, but it will sum up then become equivalent. It's like that. So because there is interaction between this parameter. Ya nanti ada chromium equivalent sama nickel equivalent gitu intinya ya. Jadi itu yang akan kita gunakan sebagai panduan. Tetapi yang paling eksak sebenarnya adalah kita harus lihat diagram fasanya gitu. Jadi percuma kalau kita punya ini kan, ini kromiumnya sekian, nikelnya sekian kan gitu kan. Nggak bisa kita hitung-hitung terus kemudian kita hitung, enggak, tapi kita cari aja fasa diagramnya gimana. Kalau diagram fasa menunjukkan ada gamma, ada austenit, berarti kita bisa bikin matensit kan gitu. Jadi setiap alloy misalnya ini ada misalnya Fe plus 2% chromium plus 1% nickel plus 1% Cr. Ini ada diagram fasanya sendiri. Yang paling betul sebelum heat treatment kita cari diagram fasanya. We will look for the diagram phase diagram. And kita lihat di situ pertama diagram fasa, phase diagram. The second is TTT diagram. Dari dua ini kita tahu kan MS-nya di mana gitu. Nah, dari situ baru kita bisa justify, selain tadi itu empirical, kita bisa justify. Yang paling betul ini kita lihat diagram fasanya dulu. Jadi kita lihat diagram fasanya. Kalau titik diagramnya MS-nya misalnya minus 200 gitu ya, berarti tidak mungkin kita buat matensit dengan alloy komposisi yang ini. Nggak mungkin bikin dari komposisi ini. Kita harus bikin komposisi yang lain supaya matensitnya bisa terbentuk. Kira-kira. Jadi individual ya, individual alloy. Dan apakah setiap alloy itu diagram fasa dan IT diagramnya beda, Pak. Beda, ya kan? Jadi satu komposisi itu satu diagram. Satu komposisi itu satu diagram. Diagram IT, satu diagram IT, ya. Jadi satu diagram. Silakan kalau ada yang perlu diklarifikasi. Sudah paham ya, Adim ya, Adim ya.
Iya, Sir. Sedikit-sedikit, Sir. Nanti saya coba pahami lagi.
Ya, ya. Tapi poin terakhir yang penting adalah kalau ada dua efek ini seperti apa kita ngelihatnya, kan gitu. Jadi poin, the important point is that we would like to modify something, right? We would like to modify something, either keep it as austenite or make it magnetite. The best way to see is that we look for phase diagram for individual alloy, for each alloy that we would like to transform into the microstructure that we would like. Okay, but our understanding about the effect of alloy alignment is especially empirical. Means that every alloy will have their role as either stabilizer or either as ferrite stabilizer or austenite stabilizer. If we mix up the both, then there will be total effect, which is not really cancel out each other, but there will be total effect. Okay, total effect. And then how we know it is actually look into the individual phase diagram. So it's like cycle now, yeah. The thinking is like cycle. So the best way to guide us into the modification of microstructure is actually phase diagram and TTT diagram. So these two things. So but actually that's the answer.
Okay, Sir. Thank you.
Okay, let's continue for a while. This is already done, I think, in Metal 1, so you can see it again. You can review that the strength of material is increased due to the alloying. I already explained it, and then see that when we would like to see it as a total impact of alloying element into the mechanical properties of alloy. Let make it a sample of a ferrite microstructure. Right, ferrite is alpha, and this is basically BCC alloy. And then if we see that most of alloying element is actually increasing the strength. Yeah. So this is basically the effect of alloying element into the mechanical properties, right? Just give you some guidance that the effect, in total effect, because we are very interested in the development of mechanical properties. That's why we are talking about the effect of the mechanical properties. But it's actually a little bit jumping. Okay, so we have a alloying element, basic alloying element. This will change the microstructure. We discussed it already. Or the effect to the and then the microstructure we can predict it with the diagram, this diagram. And then this is equilibrium and also IT. And then we have mechanical properties like hardness. Okay. So we can see here, for example, what is there? We have molybdenum and nickel. Okay, this is two things, right? This is alpha stabilizer. Nickel is gamma stabilizer. But in total, they both actually increasing the hardness, which means the original of the hardness is different things, which means that they are actually we don't care what happened in microstructure. That's what this slide tell us. That basically, if we add something into the alloying element into the steel, then they, in general, they increase the hardness. And then, how about the amount of martensit? This is actually on the hardness. So see that the percent of martensit, increasing the amount of martensit will increase the hardness. Basically, this is just logic, right? Hardness is more have a harder compared to the other microstructure. So if you have a more martensit, then which means that more hard in total. I mean, the hardness is in total will be increased. So it's not really okay. So how about the effect of alloying element into the TTT diagram? We already discussed a little bit about it, but let's see into in the detail about this. For example, we have plain carbon steel, right? We have plain carbon steel. So this still tell you that 10 means this is plain carbon. Plain carbon, it means that there is no additional alloying element other than carbon. So just carbon, okay. And then 40, this 40, this 2 digit on this symbol or names give you idea about the carbon content. This is 0.4% carbon. This is 0.4. So now if you add additional alloying element into this steel, so now the idea is that to add alloying element into this steel, now it's become the carbon content is still the same, 40 means that 0.4% carbon, and then 5.1 is tell you that there is actually addition alloying element into the steel. Okay, and what element is? It is manganese and chromium. So if you put manganese and chromium, you have another type of steel, which is 5140 alloy with so basically this is this steel with addition of manganese and chromium. And what you have is that now they are shifted to the right? This nose now a little bit going to the right, okay, and previously this here, and now it's sitting to the right, and then the MS now is previously is here, now it's shifting going down, okay. It's going to down. It's going to the left. It's going to down. So, for example, if you have a quenching mechanism like this one, okay, you quench this is here, okay. So what you have is that on the first you cannot. It's difficult for you to make it, okay. Then you do the second something like this thing. Then you will form something else rather than martensit here. But if you have this thing and then you form a martensit here, then how much martensit depend on how much temperature this quench. If it is past the MS, this is this is MS, and then MF is somewhere here, something MF. If you pass this MF, then this will be 100% martensit, right? Okay. But in this case, on the left case, you will find that we have ferrit and some perlite. You see, because you pass this line. This is how the effect of alloying element into the TT diagram and the effect of this TT diagram into the easiness for the formation of martensit. But there is a second diagram now. Okay, you put manganese now. Okay, you put manganese and chromium with the similar content of carbon, right? 0.4% of carbon now. So then you put more alloying element, in this case nickel and molybdenum. What you have is that, of course, you change the type of steel. Now it's 43, previously 51, okay? Then it's 43. This is not something that you should memorize, you just know, but you didn't memorize that thing. Okay, then 51, you see that there, the shifting is more extreme now because you put nickel and molybdenum. So the shifting now very extreme to the right. It's also shifting to the right. And then MS also shifting to the down, very shifting down here. So now the MS is start below 300, which means that if you have a cooling a curve like that, it's easier for you to make a Martin sheet in this case. So this is the idea of adding alloying element into the TT diagram and how the um, how its effect to the formation of Martin sheet, right? But as you see that the only things that can be transformed into Martin sheet is austenite, okay? So this austenite. So the area should present in the phase diagram. Otherwise, it's not possible for someone to make any Martin sheet. So this is the effect of Lang element into the IT diagram. So it's quite not difficult to follow actually. Okay. Okay, up to now, we have already discussed two things. It is the effect of Lang element into the microstructure and how they behave inside, whether it is dissolved or whether it will be formed something or any compounds, and then how we can see it this effect rather macroscopically in the diagram, which is two diagram. First is phase diagram. We know the effect of Lang element into the phase diagram, and now we also know the effect of Lang element into the TTT diagram, and we also learn the consequence of that effect into the technical procedure to make or to modify the microstructure, right? For example, from the perspective of formation of Martin sheet. Okay, up to this slide, if you already understand everything that we have discussed, that's good. Otherwise, you can ask a question, of course, if you don't really, or if you need to clarify something. We will, if not, if there is no question, we will jump just very short into further discussion on this effect of alloying element. Okay. Alloy be hardened. Okay. Therefore, you need a practical way to do it. You need Yeah, to judge. What is judge? Yeah, to judge the how easy or difficult an alloy to be hardened. Okay, you need a practical approach. This is the keyword. Okay, so therefore you should we should develop some kind of method to quantify or to compare one alloy to the other in terms of how easy they will be hardened. Okay, therefore there's new term. This we call it hardenability. So instead of discussing about hardness now, so we call it hardenability, which means that this is the ability of steel or alloy to be hardened. But the next, it's very important. Okay, so if your answer is just stop here, they will be not correct. So it should be additional word to say it. So what we call hardenability is the ability of steel to be hardened by formation of molten sheet. So it should be about molten sheet, right? Because we will measure something to do with molten sheet. It's not only the ability to be hardened, but also related to the formation of molten sheet. And then, in other words, therefore, you can also say it that the hardenability is a measure of how is uh, alloy to form molten sheet. And in some cases, it is something to do with the geometry. Okay, something to do with the geometry. So So which means that there will be different of, for example, for components, you have different size, for example, this size and that size. So your sample or your component which means that um, easy for this alloy size, because if you have that size, then this thing like this situation, then the molten sheet only on the surface and the core is not molten sheet. So which means that this size, which one is fully molten sheet, we call this is a critical size, and this is also tell you about the hardenability of the alloy. So some alloy can be very small diameter like this, can be that this big diameter like that. Okay then, so what is the factor that is the effect to the hardenability or factor affect to the hardenability? Is first is the chemical composition. The second is the structure of the steel before quenching. For example, austenite grain size, state of lying element. This is something very detailed on it. But first of all, we'll discuss about chemical composition in the beginning, as this is common things. So there are two. First is chemical composition, of course. The second is the structure or microstructure prior or before the process is done or free for the quenching. So see, this is probably the idea also why it is sometimes there is a critical size for the sample to be hardened. That's also because cooling rate in the surface and in the core is different. Sometimes in many cases in the surface is faster cooling rate, but in the core is slower cooling rate. To assess this effect of cooling rate plus the chemical composition of the steel, we use a practical approach. This practical approach, we call this practical approach. One of this is Jomini method. There is other method, but this is that's common lay use. It is a Jomini method. So what is Jomini method? It's basically some kind of procedural step, and this is standardized also. So you have standardized to do this Jomini test, basically, or Jomini methods. So what you should have is that you should make a sample from the alloy that you would like to measure the hardenability. So if you would like to measure the hardenability of steel sample, you should make sample, and the sample it should be made from the steel that you would like to measure. Okay, and then the sample is a bar in diameter. So you have the diameter, which means the cylindrical stuff with the diameter is 1 inch, 1 inch, and the length of the sample is 4 inch. Can we make it more than that? No, you should make it in this size. Why? Because it's already standardized. Okay. Okay, you can do it, of course, but it's not standardized. Then people will ask about your method, and if it's not standard, then there will be some question about it. So better to stay on the standard. If you have the sample on that standard, if not, then we can modify the standard anyway. But basically, we should keep in the standard. You should place in the picture. You see something like that. This is actually summarizing, okay? But let's see it. So you have this size, which is 1 inch. You see, this is 1 inch. But also, of course, you will make it little bit diameter on above, just to make it the sample stay still on the devices. What you should have is that you have a kind of jet, a water inlet jet. So you have a water inlet here, and the size of the nozzle is also standardized. It's 0.5, and the distance of the sample is actually also standardized. Okay, height of unimpeded water is 2.5 inch, and then the total length of the sample is 4 inch. So this is actually standardized Jomini test. So then what you should do is that you austenize the sample in some degree, probably 800 and 900 in some times. And then after you put it in the furnace, so you have a furnace 800 degree, and you put the sample here, and then you put it in the machine here, and it turn on the water jet in 24 degrees Celsius. Okay. And this is, of course, the logically there will be quench, which is very fast cooling rate in the edge, and then the cooling rate becomes slower whenever the point is increased from below or from the edge into above here. So then what you should do is that after it's cold, of course it's not hot. After it's cold already, you should treat the sample. You make this thing. You scrub the surface here on the edge, and then measure the Rockwell C hardness. So you have something like that. This is your sample. You scrub above on the position. Maybe you will have hardness laboratory work, like on the metal one. You know how to measure it, and then you measure here one by one, and every point here, and every point. and then make a plot. So let's do this thing. So you measure in the surface, something like that. You measure one by one in the distance of about 1/16 inch. And you measured it, this every point here. And you have a plot, okay, a plot, how the hardness is decreased over the length of the sample from the quench end. So this is the quench end, which is this ends. Okay, this is this ends and the ends. Of course, the logic now is that you will have a situation that the hardness will be decreased following the length from the edge. This is logic, right? Why? Because the cooling rate is different from point to point. In the beginning, they will be uh, a high cooling rate, but far away from the jet, that will be less cooling rate, or it will be slower cooling rate. So then the hardness will be depending on the distance from the ends quench. In other words, that there will be a different phase inside, right? But we just measure the mechanical properties right now, and logically you should observe that the hardness will be decreased as function of the length from the ends quench, like this. Okay, but let's see. In many cases, they will be presented like this. It will be presented like a band. Okay, it's not like one single line like this, like it's just a band of it. Why? Because there is experimental error during the experiment, of course. That's why it's minimum and maximum. This band is very useful. Just tell you that in many cases they will be presented as a band. It's not single line. But to make it easy in our discussion, we just using a line, and probably you already predicts, okay, why the hardness is changed, because the cooling rate is changed, and then because the cooling rate is changed at every point, therefore it will give you a different microstructure. For example, in the edge here, it will be very fast cooling rate like this, and what you have is matten sheet. But in the little bit far away from the end, from the edge, you have a blue, and then this is a little bit pearlite here because there is pearlite formation. Therefore, the hardness is a little bit lower. And the green one, which is a little, rather far away from the edge, you have something like that, which is a fine pearlite. You see that the hardness now is going down. If it's far away, you have still pearlite. Okay, then you have something like this. Far away here, maybe there's no change here. So you have a different microstructure. So in discussion, if we discuss back to the discussion, we say that geometry tests will assess the hardenability. Okay. Also, in the second aim is that the geometry test also assess or would like to know how much matten sheet actually form. Okay. Yeah, that's the thing. So the first is the hardness. The second is the how is this alloy to form matten sheet. Okay, so you will have this kind of different alloy sample. So let's say this is a plain carbon steel. Okay, it's 10, and 40 is carbon content. If you increase carbon content to 0.6, you have this alloy. This is just different grain size. You don't care about that in the moment. And then this is alloying element with some kind of manganese, I think. And then this is manganese molybdenum alloy, and this is probably manganese nickel alloy. You see, you have different. So what do you think? You can guess which one of this alloy. You can say the number that have high hardenability. Which alloy pose or have high hardenability? So can you guess which one? Just guess. Okay, guess is means that if you a little bit understand, then probably you'll get the point.
Maybe 43, 40, sir.
4340, right? Yeah.
Yes.
Yeah, that's correct. Why not 1060? Any idea?
Because maybe because the end, the other side of the specimen is not hard enough, sir.
Yeah, that's correct. So because it's just a guess, that I think it's just logic, right? Okay, that's important of a logical thinking or critical thinking in science, that even you don't know things, but you already have some learning or studying a little bit about this, and you know now your answer is correct. Okay, that's very important in your life, of course. Scientific justification is just actually kind of common sense. Okay, so of course, definition of hardenability is the ability to form molten sheet. This means that ability for material to make a molten sheet, right? And then it means that 4040 is something that quite stable now. The formation of matter is quite easy. Even you go into deep into the sample. So this is basically the definition of hardenability. How deep it is the sample to be hardened, So um, this is the answer will be 4340. Okay, and then less hardenability or less ability to be hardened is 4140. Okay, that's the easy. And why not 1060? Even though you see that the hardness in the beginning is very high, but it is very fastly jump into the very low hardness, which means that the molten sheet will be somewhere here, and then you have no molten sheet anymore after this distance. So which means that in the perspective of hardenability, it is this alloy is not easy to be hardened, because the molten sheet only form in the edge, it's not goes into the depth of the sample. So that's the meaning of hardenability. So hardenability is something to do with the ability to form molten sheet, and the ability of the steel to be hardened, and the ability to form the molten sheet in relation to the size, in the depth of the sample. So in the depth of the hardness from the edge. So let's call it the easy term is the depth of the molten sheet. Okay, the depth of molten sheet. Okay, that's correct answer. That's pretty good because you just use your guessing. It's also the same thing. This is just the similar figure. Just give you any. But it's more challenging to see this one, right? Rather than this one. This is pretty easy and quick answer. This 4340. This, of course, there's not debatable. That's easy. But yeah. Of course, then you can that similar logic. If you add alloying element, then of course going to the right, which means that higher amounts of alloying elements make easy for you to be hardened. Why it is? Yeah, it is easy. It's familiar. If you put another cooling here, then still you have some martins, right? Then if you ship it again to, for example, here on C curve, and you have more molten sheet, of course. Even the cooling rate is rather slowly compared to uh, the blue one. So of course, logically, of course, you can think that addition of alloying element will make alloy easy to be hardened, or in other language, the hardenability of steel will be increased as the alloying element is increased. So that's the things. This is a bit challenging situation. If you have alloying, if you have a starting point with similar a similar alloy, okay, and this thing let's okay. This is basically this other say that avoid the perlite formation. Okay, then if you would like not to have a perlite reaction, then what you should have is that this is transformed to martensite. If you need to have martensite transformation, then shifted the curve to the right, right? Shifted to the right. So this is the original, shifted to the right. Why? How you add alloy element? It's just another saying or another word or another term or another description of what we have already discussed. The second is that grain size. So this is quite new for you probably, and I need to little bit discuss about this. There's let imagine that you have outstanding microstructure like that. This thing with 3 grain. This is call alloy A, and then you have alloy B, which is finer grain size, something like that, more fine or finer grain. This is exactly similar composition. Similar composition, right? So you have a large grain size. Then, all right, let's start the smaller grain size. So the austenitic to pellet is something you should avoid. Something you should avoid. Okay, and then austenitic to pellet, it's easy if you have a smaller grain size, which means many boundary. Many boundary mean that pellet will be initiate here. That's easy if you have so many grain. For you to have this transformation, it's easier occur when you have this microstructure. And it is difficult if you have less grain boundaries, which means you have this kind of microstructure. So for A and B, now it's easier for B to make a pellet, which means that's not easy to form martensite. It's not easy for A to make a pellet, that's easier to form martensite. So therefore, increasing the grain size will be easy for you to make martensite. This is the effect of grain size. So we can see it in here. Especially for the graph here, so that you see that if you increase the grain, increase the not this first, this thing, sorry, this thing. So if you increase the grain size, the martensite start will be increased, okay, something like that. So which means that increasing grain size will ease for you to make martensite. Martensite start increase, easier for you to make a martensite. There is another logic of this thing, but basically same idea. So basically you can use this idea, okay, you can use this idea. And then another effect, in addition of the grain size, there is another effect, which is austenitization temperature. You see, you have something like that, okay. You have something like that. This is a curve, okay, for the temperature, and this is carbon content. And then you will ask question, whether I austenize and at this temperature, which is 800, and then either here 900 give a different result. if you austenizing temperature is different, either 800 900. The answer is this curve. Increase as the temperature austenitization is increased. So basically, the effect of temperature austenitization temperature is actually the effect of grain size. Okay, so in many ways, the explanation is here already. So if you have a low temperature austenitization here, you have something like that. If you increase further, and then your grain size will grow, and then they will increase the size, and it is easy to be hardened, something like that. So basically, this is just effect of grain size. The increasing austenite grain temperature will increase the grain, and you have increasing hardenability. Okay. A little bit, yeah, little bit. Maybe we have the effect of surface cracking on the next slide. Just be patient on it. I will explain later on. You see that we can have different cooling medium for quenching. Quenching, you can use either air, oil, or water. Okay, and then air will have a low severity, which means that cooling rate is quite slow. Oil is moderate. Very high is actually water. So if you have something like that and you make it cooling rate something like that, you should use water. If you have you want to have it here, you should have oil. If you have a little bit slow, you can use air. And then hardness, of course, is low, and then it's moderate and high. So what is the effect of surface to volume ratio? Which means that if you have a box like that, compared to this thing, then it's easier to be for you to make a hardenability with cylinder form like that. Okay, rather than in the box, because surface to volume ratio it is actually higher for the cylindrical rather than this box, something like that. So this is effect of geometry. So if you have component like a box and component like cylindrical, then easier for you to make to harden the steel with this geometry rather than this geometry. So this just tell you a little bit about the effect of geometry. So it's all about the surface to volume ratio. Okay, surface is very important. Why? Because everything is start from the surface. So start from the surface and going to down to the core of the sample. So there is some practical stuff to consider, but the summary from the slide about the hardenability test is that you should do it with specific procedure, which is actually standardized. And then the second is that you will have kind of result, which is a plot of hardness function of a depth from the edge of the sample. And this curve will tell you whether the alloy have a higher hardenability or not. And then this also affected by the grain size, and the grain size is affected by temperatures. And then there is something else you need to consider is the geometry of the sample, and then practically the medium that you will use for doing quenching. So that's, I think, all for today. Next week we will discuss about the heat treatment, and then we need to set up the quiz but I haven't arranged it yet. But just be prepared for every week. Okay, probably next week you see. Just be prepared. I already put all these slides in classroom, and if you have any question furthermore, you can also ask a question. Since it is quite it's actually fair enough because we have already lecture to have a quiz, but I promise you to give the slide. So I haven't sent it yet last week, but today I already put it in the classroom. You can check it, you can find it. So next week, it's fair enough if you have some quiz for first evaluation. Okay. Any question?
Izin bertanya, Pak.
Ya, silakan.
Tadi sepertinya ketika austenizing temperatur, koneksi internetnya sedang jelek, jadi keputus di bagian situ. Apa boleh diulang, Pak?
Ya, austenizing temperatur itu akan mempengaruhi grain size. Itu aja sih intinya. Sehingga kita bisa lihat di sini ini kenaikan ya, austenisasi temperatur. Temperatur austenisasinya tinggi, dia lebih punya hardenability yang lebih baik, yang warna biru ya, dibanding dengan warna yang brown. Karena kita naikkan temperatur austenisasinya. Kenapa begitu? Karena ada hubungannya dengan grain size. Kalau kita naikkan temperaturnya, maka grain size-nya akan lebih besar. Lebih besar kayak ini. Sehingga dia lebih gampang membentuk marten sheet. Intinya itu sih. Ya, kira-kira begitu. Nanti rekamannya mungkin semoga saya bisa share. Gitu kira-kira. Jadi semakin tinggi austenisasinya, maka semakin tinggi grain size-nya, maka akan semakin memberikan hardenability yang lebih baik gitu. Dan gambar itu adalah di gambar slide